All right, welcome everyone to our sixth geometry topology summer school, which is hosted at Feza Gürsey Institute in Istanbul this year. Our first lecturer is Madnick from Taiwan, and he's going to talk about holomorphic curves in the sixth sphere. So thanks him for accepting our lecture invitation.
Well, thanks for the invitation to speak here. It's a pleasure. And looks like there's some really great talks lined up, so I'm looking forward to learning from the other speakers as well. So, right, let me give an overview of what I'm going to be talking about in these 4 lectures. So we're going to have 4 lectures, and the first 2 will be completely expository. So if you are an expert in G2 geometry or nearly Kähler geometry, and you know all this, then maybe Monday and Tuesday's talks will not be that interesting to you. You can go to sleep. But Wednesday and Friday, this is all background for Wednesday and Friday, where I'll talk about some recent work that I've done on closed holomorphic curves in the 6th sphere, and also some free boundary holomorphic curves more generally in nearly Kähler 6 manifolds. So lecture 1 ended up being a little too long. And lecture 2 ended up being a little too short. That's just the way it turned out. So today I'll cover parts 1 and 2 of lecture 1, and then tomorrow we'll pick up with part 3 of lecture 1 on associatives and co-associatives, and then go into lecture 2. Okay, so what are we going to talk about? I'm not going to assume any background beyond basic Riemannian geometry. So we're going to talk about what is the holonomy group of a Riemannian manifold. We're going to define it, talk about its properties, and the classification of holonomy groups due to Bergers. Then we'll use that as sort of motivation for G2 geometry. And G2 is really tied up with the Octonians. So we'll very briefly review what the Octonians are and how they relate to G2. And using that, we'll define G2 structures on 7 manifolds and explain how G2 structures are related to G2 holonomy. Okay, then we'll give just a few examples. We'll give maybe some of the historic examples that have provided a lot of motivation for the field. But these days there are many examples of G2 manifolds, and I won't really have time to survey everything. I just want to give some overview of maybe the most influential examples. Okay. Now, I was originally hoping to talk about the submanifolds today, but I think I'm going to move that to tomorrow. So tomorrow we'll talk about the submanifolds in 7 manifolds with G2 structures. We'll talk about associative 3-folds and co-associative 4-folds. Okay. So let's get started from just the very beginning. So let's let M be a connected Riemannian manifold of dimension n, and let's let gamma be a loop based at a point x. So given this loop gamma, we can consider the parallel translation map, P sub gamma. Okay, it inputs a vector at x, you parallel translate it around gamma, and you get back some possibly different vector at x. Okay, P gamma is not necessarily the identity map. It could be the case that when you do this parallel translation around your loop, you get some other vector. And you can collect these parallel translation maps into a set. So you can look at the set of all parallel translation maps where gamma ranges over all possible loops at x. Okay, and this set is not just a set, as I'm going to explain, it's actually a group, and it's called the holonomy group of G at x. It records both geometric information as well as topological information. But if you're a geometer, maybe you're only interested in the geometric information, and you can sort of kill the topological information by removing any contributions from the fundamental group. So this is the concept of the reduced holonomy group, where you only consider loops which are null homotopic. Okay. Now these sets really are groups. They're groups for the same reason that the fundamental group is a group. The group structure is via loop concatenation. So you go around one loop, then you go around the next loop. Okay, and the inverse of P alpha is just parallel translate around alpha, but the other way. Okay, and since parallel translation is an isometry, these groups are not just subgroups of GL, but they're actually subgroups of the orthogonal group. Okay, and Okay, now you might worry that this definition depends on the base point, but it doesn't really. Again, just like the fundamental group, if you have a path from X to Y, then the holonomy group at Y is conjugate to the holonomy group at X. So we can speak of the holonomy group and reduced holonomy groups just as groups without reference to the base point, provided we understand that they're groups defined up to conjugation. Okay, so some basic properties are that the reduced holonomy group is connected. It is a normal subgroup of the full holonomy group. And notice that if M is simply connected, then the two coincide. And the reduced holonomy group is in fact the identity component of the full holonomy group. Okay, so these are some very basic properties. And maybe a deeper, more difficult to prove fact is that in fact the reduced holonomy group is a closed Lie subgroup of SON. This is due to Borel and Leishnerowitz. So taken together, what we learn is that the reduced holonomy group is a compact connected Lie group. And so since it's a compact connected Lie group, you can talk about it's interesting to talk about its Lie algebra. So its Lie algebra will be called the holonomy algebra. It's contained in a little SO of TXM. And there's a standard isomorphism between the skew symmetric matrices and the two forms. Okay, so you can think of the holonomy algebra at X as being contained in the two forms at X. We'll use this fact on the next slide. And I should point out that the holonomy group, or the reduced holonomy group, it's not just an abstract group, it has more structure than that. It comes with an embedding into SOTXM, right? So because there's an obvious action of the reduced holonomy group on TXM, okay, and it's a linear action. And so the point is that you can think of the reduced holonomy group as a representation. Okay, and this point of view will be important later. Okay, so who cares, right? Well, why is the holonomy group of a Riemannian manifold interesting or important? What does it tell us? So the answer is that there's well, it tells you at least three things. So it's related to the curvature of your manifold. It's related to the presence of parallel tensor fields or parallel spinor fields, and it's also related to the presence of extra geometric structure. So extra structure on your manifold that is compatible with your metric. Okay, so I want to discuss each of those to give you a sense that this really is something we should really care about. So how is the holonomy related to the curvature? So let's recall that the Riemann curvature tensor is a 4 tensor. So it lives in T star tensor 4 times. Here I'm just abbreviating notation by I'm letting T be the tangent space at X. So the Riemann curvature tensor at X is a 4 tensor, but in fact, it lives in a subspace of the 4 tensors because it has various symmetries. Okay, you can swap the first 2 indices and then you get a minus sign. You swap the last 2 indices, you get a minus sign, and so on. So the Riemann curvature tensor lives in this subspace. But in fact, it actually lives in an even smaller subspace than that, and that subspace is dictated by the holonomy algebra. So remember that the holonomy algebra is contained in lambda 2. So the point is that the holonomy algebra constrains the Riemann curvature tensor. Right, so the smaller your holonomy algebra, the more constraints there are on your curvature. So for example, if your holonomy algebra is 0, then your Riemann curvature tensor must be 0 and your metric is flat. Conversely, not only does the holonomy constrain the curvature, but in fact the holonomy, in a sense, determines the curvature, it generates it. Okay, this is the Ambrose-Singer theorem. Okay, it says that the holonomy algebra is spanned by curvature endomorphisms, or more precisely, it's spanned by conjugates of the curvature endomorphisms, where the conjugates are parallel translation maps. Okay, so this explains the common slogan, holonomy is curvature. Sometimes you'll hear that. Okay, it's also related to the presence of parallel tensor fields, right? Very frequently in differential geometry, we benefit from having parallel tensor fields or parallel differential forms. And whether these things exist, this is completely determined by the holonomy representation. So this is sometimes called the holonomy principle, kind of a non-descriptive name. So just fix a point X, and the statement is if S is a parallel tensor field, then S at X is fixed by the holonomy action on the tangent space. And conversely, if you have a tensor at a point, which is fixed by the holonomy action, then you can extend it uniquely to a parallel tensor field on the whole manifold. Okay, so again, this applies to vector fields, covector fields, differential forms. There's also another statement for spinor fields. but I won't state it. Finally, I should mention that the holonomy is related to the presence of extra geometric structure. So I'm not going to define exactly what I mean, but what I mean is the following theorem. Let's say you have a Riemannian n manifold and G is a subgroup of O of n, then the holonomy of G being contained in your Lie group G, this is equivalent to the existence of a so-called G structure that is compatible with your metric and torsion-free. Okay, I'm not going to define what these words are, G structure or metric compatible or torsion-free, but just to give you some sense as to what this means, I'm just going to give you maybe the standard example. So let's say you have an even dimensional Riemannian manifold and you take your group G to be U of n over 2. Okay, so this fancy phrase, a torsion-free U of n over 2 structure, that's a very fancy way of saying a Kähler structure. Okay, and so that's just a pair metric, comma, J, where J is a parallel orthogonal complex structure. And what this theorem says in this case for G equals U of n over 2 is that the holonomy is contained in U of n over 2 if and only if G is a Kähler metric. So the point is that if you have your Riemannian manifold and you wanted to know, is my metric G secretly a Kähler metric, right? Does it come from some Kähler structure where, do I have a parallel orthogonal complex structure? This is equivalent to the holonomy being contained in U of n over 2. This is maybe the simplest example of this theorem. Okay, so hopefully this convinces you that the holonomy group is very fundamental to Riemannian geometry and to the theory of sort of special geometric structures on manifolds. So what you'd like to do ideally is to classify as much as possible the possible holonomy groups. So a good place to start would be with products. And it's not too hard to show that if G is a product metric, then the holonomy group splits as a product. And it turns out that a converse to this is true, but you have to be a little careful how you state that converse. Let's introduce some words. Say that a metric G is globally reducible if it's globally a product, locally reducible if it's locally a product, and irreducible if it's not locally a product. And so what this fact says above here is that if G is globally reducible, then the holonomy group is a product of holonomy groups. And not only that, but the holonomy representation is reducible. And so phrased this way, there's a converse. So this converse is called the Durham decomposition theorem, and there is a local statement and a global statement. So we're going to assume that the holonomy representation is reducible as a representation, right? Meaning that there's some non-trivial proper invariant subspace. The local statement says that the reduced holonomy group is therefore a product group. Okay, not necessarily a product of holonomy groups, just simply a product group, and the metric is locally reducible. The global statement says if you further assume that your metric is complete and your manifold is simply connected, then more is true. Then not only is the holonomy group a product group, it's a product of holonomy groups. And in fact, your metric is globally reducible. Okay. From a certain point of view, this is somehow very similar to what was on the previous slide about extra geometric structure if you regard kind of a product structure as extra geometric structure. There's a sense in which that's true, I think. Okay, so this takes care of the case of products, and it means when we classify holonomy groups, we should really stick to the case where the metric is irreducible. And in fact, where the representation is irreducible, really. So another case of interest is that of locally symmetric spaces. So let's recall that a Riemannian manifold is locally symmetric if the Riemann curvature tensor or curvature endomorphism is parallel with respect to the Levi-Civita connection. Okay, this is equivalent to saying that the Riemannian manifold is locally isometric to a simply connected Riemannian symmetric space. And there's a whole theory of these things. It's very beautiful and also very intricate. But all I want to say is that the simply connected Riemannian symmetric spaces are completely classified and by Cartan, and in fact, their holonomy groups are known. So therefore, the holonomy groups of locally symmetric spaces are classified. So this takes care of the classification in the case where the metric is locally reducible or locally symmetric. That leaves literally every other metric. So what can you say about all other metrics in the world, ones which are not locally a product and not locally symmetric? So what you can say is due to Bergers. This is sometimes known as Bergers' list. Okay, so let's suppose you have an n-dimensional simply connected Riemannian manifold, and let's suppose that G is not locally reducible and not locally symmetric. Then the holonomy group must be one of the following groups. Okay, on this table, it can be SON, U of n over 2, SUN over 2, SPN over 4, SPN over 4, SP1, G2, spin 7, or spin 9. Okay, these are the possibilities for the holonomy groups. When Bergers proved this, the only holonomy groups that were known, I believe, were, other than the generic case SON, the only cases that were known, I think, were the unitary groups and SU2. It was sort of it was an open question as to whether any of the other groups actually occurred, right? Bergers didn't prove that these groups actually occurred. He just showed that these are the only possibilities. Okay, and in fact, one of the first things to happen after this in this direction was a theorem of Alexievsky and also by Brown and Gray, which says that if your holonomy is spin 9, then in fact your metric is symmetric, and therefore spin 9 shouldn't be on the list. So given that, it's reasonable to conjecture that maybe G2 and spin 7 shouldn't be there either, and maybe the others also don't belong. Okay, but over the course of many decades, a lot of hard work by many mathematicians proved that in fact there do exist manifolds, complete examples, and now even compact examples with all of these given holonomy groups. So all of these groups do in fact occur. Yeah, I should mention that this theorem was originally proved by Bergers, but then there were other proofs given. Jim Simons proved this theorem a different way in his PhD thesis. I think he observed that this is precisely the list of groups which act transitively on spheres. And then I think using that idea, yet another proof of Bergers' list was given by Carlos Olmos more recently, I think in the 2008 or something. Okay, so all of these groups occur, and in fact, many of these groups, many of Riemannian manifolds with these holonomy groups are known by other names. So for instance, if the holonomy, as we've mentioned, is equal to U of n over 2 or contained in U of n over 2, we call those manifolds Kähler. Okay, if the holonomy group is equal to SUN over 2 or contained in it, then we call it Calabi-Yau, so on and so forth. One reason to care about these things is that, as we mentioned before, the holonomy places constraints on the curvature. And this manifests in a very beautiful way, in fact, in that these manifolds with special holonomy, so one of these down here, all of them are Einstein, and many of them are Ricci flat. And as probably all of you know, Einstein manifolds, and in particular Ricci flat manifolds, are very, very, very hard to find, especially compact ones. Speaking of compact Ricci flat manifolds, the only compact Ricci flat manifolds that we know of that aren't flat are on this list. So every known example of a compact Ricci flat manifold, which isn't flat at the moment, is either Calabi-Yau, hyperkähler, G2, or spin 7. It's rather striking that we don't know any examples of a compact Ricci flat manifold with generic holonomy SON. That's a very striking fact, and there are conjectures either way. You might also notice that the only odd number on this list is 7. And so based on what I just said, another open question is, are there compact Ricci flat 5 manifolds which aren't products or symmetric spaces or flat? So this is another open question. We don't have any compact Ricci flat manifolds in odd dimensions other than, I guess, the trivial 1 and 3, and then the G2 examples in dimension 7. Now, how should we think of this list? There's many different ways you can sort of organize it. You're thinking based on maybe Ricci flatness or the Einstein condition, but the way that I like to organize my thoughts is that based on the norm division algebras. So in a certain sense, these two groups in the even dimensions correspond to the complex numbers, the next two correspond to the quaternions, and the last two correspond in a certain sense to the Octonians. Okay, so given the relationship that I claim between G2 and the Octonians, that is what we're going to talk about now. I'd like to explain exactly how the group G2 relates to the Octonians, and then we'll use that to talk about G2 holonomy on 7 manifolds. Okay, so this is what I was saying. G2 is related to the Octonians, so there's a bunch of ways to see this. So here's one. Let's let A be a normed division algebra. I'll define that word on the next slide. And let's consider its automorphism group. This is the set of invertible linear transformations which preserve the product structure. Then it's a classical fact, I guess, that the automorphism group of R is the identity. That of the complex numbers is Z2, the quaternions is SO3, and the octonians is G2. So if you like, you can take this to be the definition of G2. And already this kind of gives a sense as to maybe what G2 means geometrically. If you think of the quaternions as having a real line and then an imaginary part that's sort of a copy of R3, then in a sense, the way that SO3 relates to the imaginary quaternions is somehow kind of similar to how G2 relates to the imaginary octonians, which is R7. Right, so there are these sort of analogies between geometry in dimension 3 and geometry in dimension 7. I'm going to hammer that point home more in the next lecture. But if you like, you can take this as the definition of G2. Okay, so what is a norm division algebra? It is a pair consisting of a finite dimensional R algebra, not necessarily associative, but with a unit, together with a positive definite inner product for this talk, and the norm respects the multiplication. Okay, so there's a whole theory of these things, but I'll spare you the details. The upshot is that there's only 4 of them. The only norm division algebras, it's a beautiful fact due to Hurwitz, are R, C, H, and O. The real numbers, complex numbers, quaternions, and octonians. So roughly, how would you prove this? There's a process known as the Cayley-Dickson process. And what that does is it is the process by which you go from R to C. So you can think of complex numbers as pairs of real numbers, and there's some weird product you can define. And then you can iterate that, and you can think of the quaternions as pairs of complex numbers with a weird product, the octonians as pairs of quaternions, and etc. So there's some sort of doubling construction known as the Cayley-Dickson extension process. And using it, you can go from R to C to H to O. And it turns out that other than R, a priori, every norm division algebra, if you didn't know Hurwitz theorem, every norm division algebra other than R is the Cayley-Dickson extension of something else. So if you know that every norm division algebra is the Cayley-Dickson extension of something else, then you can show that if you start from R, you can kind of build up. And what happens is at every stage you lose properties until eventually you're no longer a norm division algebra. Okay, so that, in very, very rough terms, is essentially the proof of Hurwitz's theorem. It proceeds by this Cayley-Dickson process of doubling. I should point out that some authors have a slightly more general definition of norm division algebra. They allow for not just positive definite metrics, but arbitrary non-degenerate metrics. And in that case, you'll get more norm division algebras. You'll get what are called the split complex numbers, split quaternions, and split octonians. This is a very interesting thing, but I'm going to stick to the positive definite case. Okay, so the most unhelpful definition you could make is that the octonians are the norm division algebra, which are not R, C, or H. You could also say that they're the norm division algebra, which are not associative. Okay, can everyone see everything? I'm getting some weird notification. Everything's fine, right?
Yeah, fine. Great.
Okay, Zoom just gave me some weird notification.
Oh,
okay. So,
no problem, Peter.
Okay, it's fine. Thanks. Okay, so yeah, so this is an unhelpful definition of the octonians. Let's give maybe a better one. So a more helpful definition comes from the process I just described, this Cayley-Dickson extension. You can think of it as the Cayley-Dickson extension of the quaternions. So octonians are pairs of quaternions with addition defined in the obvious component-wise way and multiplication defined like this. Okay, now since quaternions are non-commutative, you have to be careful with the order of the factors, but okay. And the inner product is the one you think it is. It's the flat one on R8. Okay, but the definition that I and many people kind of actually use in practice is this. It's just the span of these 8 elements. Okay, the number 1 and 7, oriented orthonormal vectors. And so an octonian is just something like this. Okay, and addition is defined in the, again, the obvious way, and the multiplication is defined by this table. I should say a few things about this table. So first of all, this convention is not standard. Okay, this is this convention that I use and that Dominic Joyce uses, and I think Robert Bryant uses, but certainly other authors use other conventions, and everyone feels very strongly that their convention is the right one. Notice I've colored the table in a particular way to highlight certain patterns. So if you take E1, E2, and E3 and you multiply them by E1, E2, and E3, then either you get -1 back or you get plus or minus E1, E2, or E3. Okay, contrast that with what happens when you multiply E4, 5, 6, 7 with E4, 5, 6, 7. In that case, you don't get 4, 5, 6, 7 back, you get, again, 1, 2, 3. So this is, I guess, kind of like there's like an even and odd type thing happening where, like, if you add two even numbers, you get an even number. And, you know, it's that kind of pattern that you're seeing here between 1, 2, 3 on the one hand and 4, 5, 6, 7 on the other hand. This splitting here into 3 plus 4 is very, very fundamental to G2 geometry, and it's particularly fundamental to the study of associatives and co-associatives. So I'm going to come back to the pattern in this table in a pretty crucial way next lecture. Okay, so just some algebraic facts about the Octonians, just to make us a little more comfortable with what's going on, and also to set the stage for G2 again. So you can split the Octonians. You can think of the Octonians as a copy of R8, and you can split it orthogonally as a real line, okay, just the span of the number 1, and its orthogonal complement. These are called the imaginary Octonians. It's a copy of R7. And so you can write every Octonian as a real part plus the imaginary part, and then its conjugate is defined as you think it would be. It's the real part minus the imaginary part. So you can recover the real part from X and its conjugate. You can recover the imaginary part from X and its conjugate in the obvious way. The only thing you have to worry about is that when you do XY bar, that's Y bar times X bar. And again, octonionic multiplication is not commutative. So this is a place where you can make errors if you're not careful. Octonionic multiplication relates to the inner product in a very nice way. I won't read these at you, but these are some useful identities should you ever need to do some calculations. But one thing I must emphasize is that octonionic multiplication is not associative. The addition is, but the multiplication is not. However, it does satisfy a weak form of associativity known as alternativity, which is to say that it's associative on when two of your three elements are the same. So it's not associative on X, Y, and Z, but it is associative on XXY, XYY, and XYX. Okay, so there's this weak form of associativity that's somewhat useful. Okay, so what we're going to focus on is the imaginary Octonians. That's a copy of R7, and this is the linear model for the types of manifolds that we want to consider. Okay, so if you want, what I'm about to describe are sort of the tangent spaces of the manifolds that we're going to look at. Okay, so what's special about the imaginary Octonians? For one thing, it carries a vector cross product, the so-called 7-dimensional vector cross product. This is very much like the familiar vector cross product in R3, which itself arises from the imaginary quaternions. Right, so just as the ordinary cross product in R3 comes from the imaginary quaternions, the so-called 7-dimensional cross product arises from the imaginary Octonians. Okay, what do I mean by saying it's a cross product? All I mean is that this operation here, it's alternating, and X cross Y is orthogonal to X. It's also orthogonal to Y. And its norm is what you hope it would be. It's the area of this parallelogram. Now, you can encode this vector cross product in a very useful way. You can recast it as a 3-form just by lowering an index, okay, and using the metric. So you can get a 3-form like this. This is called the associative 3-form. I'm going to denote it phi0, and it's basically the same information in the presence of the metric as the vector cross product. Okay, the name associative will be justified next lecture. At the moment, it's not really clear why the word associative is there. It's also not obvious a priori that this is really a 3-form, but you can check that, in fact, this object is really alternating in all of its arguments. Okay, so what does phi0 look like in the standard basis, let's say? So if you take the standard basis of the Octonians, that's a copy of R8, so 1, E1 up to E7, then phi0 has this horrible looking expression. Here, E1, 2, 3 is shorthand for E1, wedge E2, wedge E3, etc. Okay, now these numbers are not arbitrary. These numbers that appear here are in fact the multiplication table for the Octonians. So for instance, E1 times E2 is E3, or E2 times E5 is negative E7. So if you ever forget the multiplication table, this is how you could remember it, I guess. So the analogy, which is very, very fundamental, it's certainly very fundamental to the study of associative threefolds, is this. You know, in Cn, what we're familiar with is, you know, you can think of Cn as R2n, and you have this complex structure J, and from J you can build the so-called Kähler two-form omega. And we've done something very similar. We have an object that's kind of like J, which is the cross product, sort of, and from the cross product we've built this three-form. This analogy is actually better than it looks. There really is a very strong analogy between the pair J omega on the one hand in even dimensions, and the cross product and phi0 on R7. Okay, and there's a lot of work done really motivated just by this analogy, just thinking of the cross product as somehow like J and phi0 as somehow like the Kähler form. Okay, so we want somehow a more intrinsic understanding of the form phi0. Okay, and what we want to know is this: if you have some three form on R7, is it the same as phi0 up to change of coordinates? Right? I mean, after all, you know, there's many conventions for the, you know, the coordinates on R7 in a sense. That there are many different conventions for phi0. Kind of, how would you know if you have two three forms? How would you know whether one of them is really the same as phi0 up to some change of coordinates? Okay, so to answer this question and to further elucidate the relationship between the imaginary Octonians and G2, just I'm going to need some more words. So for each three form gamma on R7, we're going to define the symmetric bilinear form B gamma. Okay, so this inputs two vectors and it's symmetric, and it outputs a 7 form. Here iota is the contraction, right? This is Y hook gamma, if you like. And we'll say that a three form is definite if this B gamma thing is definite. Okay, and you can let lambda 3 plus V star be the set of definite three forms. Okay, so these are the set of all three forms for which this thing is definite. So an example of a definite three form is, as you might suspect, phi0. Okay, the upshot for now is that if gamma is a definite three form, then this object here, you can write it like this. It's equal to G gamma XY times the volume form. So the point is that when you have a definite three form, you automatically get an induced positive definite inner product G gamma, and also an induced orientation form on R7. Okay, so let's consider this change of coordinate action. So there's this GL7R action on R7 given by change of coordinates, and this induces in turn an action on lambda 3, again by change of coordinates. And so you might ask, what are the set of three forms which are the same as phi0 up to change of coordinates? And it turns out that those are exactly the definite three forms. Okay, so that's sort of the most intuitive way I know of explaining this very fundamental fact of G2 geometry. Okay, the orbit of phi0 under this GL7R action is exactly the set of definite three forms. Okay, so this being an orbit of a group, you can think of it as a homogeneous space. This is GL7R mod some stabilizer. What is the stabilizer? The stabilizer is in fact exactly G2. Okay, so this set of definite three forms is really isomorphic to GL7R mod G2. And as far as G2 geometry is concerned, this is, for practical purposes, maybe the most useful definition, if you like, of G2. And, you know, as Robert Bryant would say, this illustrates that G2 is, in a sense, not really that much of an exceptional group. It's almost more like a classical group. If you think of the orthogonal group as the set of matrices which preserve a, you know, an inner product, positive definite inner product, you can think of the unitary group as the set of matrices which preserve the Kähler form and the metric and the complex structure. So too, you can think of G2 as the set of 7 by 7 matrices which preserve some very natural geometric object, in this case, the associative three form. Okay, it's sort of a very down-to-earth understanding or description of G2. And so an interesting corollary is this. So if you remember that this is a again, lambda 3 plus of V star, the set of definite 3 forms. This is GL7R mod G2. So you count dimensions and you find that this set has the same number of dimensions, 35, as lambda 3 of V star. And so the corollary is that this is in fact, the definite 3 forms are an open set in R35. This is a pretty rare thing to have the orbit of some form be open in its ambient space of forms. This is a very rare thing, and we say that phi0 is a stable form. I think this terminology is due to Hitchin. I believe the stable forms, which is to say the forms whose orbits under this action are open, I believe such forms are classified. And if I remember correctly, it's a very short list, and phi0 is one such thing. So this is somehow a very special feature. Okay, so that was the linear story. In a sense, that what I just described was what we want to happen on our tangent spaces. Okay, so let's talk about the nonlinear version. Let's move finally to manifolds. So if you have a smooth 7 manifold, we'll say that a G2 structure on M7, R7 manifold, it's the definition is that it's a definite 3 form. And what I mean by that, it's a differential 3 form that's definite at each point. And just to remind you, what that means is that at each point in M, this symmetric bilinear form is definite. But by what I said on the previous slide, by the considerations that we just talked about, this is equivalent to saying that at each point in M, there's a linear isomorphism between the tangent space and R7 that identifies phi at x with the sort of flat associative 3 form phi0. Or to say that yet again, at each point in X, there's a frame at X such that phi at X can be written kind of in this standard way. Okay. So this, the upshot is that this gives a sort of a very concrete geometric way of thinking about what a G2 structure is. It's basically an identification of each tangent space with the imaginary Octonians. So you think of each tangent space as the imaginary Octonians, and the identification is such that to 0th order, phi at x looks like the flat associative 3 form phi0. Okay, that's basically the idea. And this is to 0th order, right? Where we haven't taken any derivatives yet. All of this is somehow just on the linear level. Okay. And because we haven't introduced any derivatives, the question of whether a 7 manifold admits a G2 structure, this is a purely topological question. Right, it's kind of like asking when does an even dimensional manifold admit an almost complex structure or something like that. It's purely topological, and in fact, M admits a G2 structure if and only if it's orientable in spin. Okay, so a G2 structure, however, unlike an almost complex structure, a G2 structure gives you sort of more data than maybe you might want, and sometimes. Because G2 is contained in SO7, every G2 structure induces both a canonical Riemannian metric and an orientation. Right? This is what we said previously about definite forms inducing a metric and an orientation, and it comes from this formula here. Okay, this single formula picks out both the metric and the volume form. And then there's this very pretty expression for the volume form in terms of phi wedge star phi. Okay. And if you take your 3 form and you raise an index, then you get a cross product operation. So again, each tangent space, because we're thinking of it as the imaginary Octonians, has a 7-dimensional vector cross product. And there are some authors who will sort of say that a G2 structure is this 7-dimensional cross product structure, and it's essentially the same thing. Okay, so several warnings. First, this correspondence that takes a G2 structure and outputs a Riemannian metric, that is not injective. And so that means that different G2 structures can induce the same metric. These are sometimes known as isometric G2 structures. There's a flow for such things. And it's very interesting, but you do have to worry about this issue. I should point out also that this map is very nonlinear. This is somehow, these are contrasts from the, let's say, the almost complex case or the Kähler case. And finally, this Hodge star is determined by, of course, the metric and the volume form, but those depend non-linearly on phi. So, star depends on phi, and star depends non-linearly on phi. That's the point here. Okay, So a question that comes to mind is, what does any of this have to do with G2 holonomy, right? Well, what do G2 structures have to do with G2 holonomy? So to answer that, we're going to introduce some calculus. Okay, so we'll say that a G2 structure is closed if it's closed. We'll say it's co-closed if it's co-closed, and it's torsion-free if it's both closed and co-closed. Okay, this is sort of standard terminology. And terminology which is less standard is this. We'll say that a G2 manifold is a 7 manifold with a torsion-free G2 structure. Okay, there's some disagreement as to what a G2 manifold ought to be. I think at the moment, this is the consensus for what a G2 manifold ought to be. Some people say the definition of a G2 manifold ought to be weaker, some say stronger, but I think this is the most commonly used one at present. Okay, it's a 7 manifold with a torsion-free G2 structure, so phi is closed and co-closed. Notice that in this definition, R7 with its flat G2 structure, phi 0 is a G2 manifold. Okay, but its holonomy group is, of course, trivial, the identity. Okay, so this raises the question of what exactly is the relationship between being a G2 manifold and having G2 holonomy. This is answered by a theorem of Fernandez and Gray. And it goes like this. Let's say M is orientable in spin. If you have a G2 structure that's closed and co-closed, then the holonomy group of your induced metric is contained in G2. And conversely, every Riemannian metric with holonomy contained in G2 arises in this way. So if you have some arbitrary metric on your orientable spin 7 manifold, and if the holonomy is contained in G2, then in fact, G is the induced metric from a G2 structure, which is torsion-free, okay, closed and co-closed. So the way you would prove this is by using the holonomy principle, basically to recast the holonomy contained in G2 condition as the parallelism of phi with respect to the Levi-Civita connection. So what you really are asking is, when is the 3-form parallel with respect to the Levi-Civita connection? And then what you do is you take knob of phi and you decompose it into G2 irreducible components. And when you do this G2 irreducible decomposition, you find that d phi and d star phi completely determine the covariant derivative of phi. That's kind of a surprising thing. Really, it doesn't happen necessarily for other geometric structures that d and d star control the exterior derivative, the covariant derivative, rather. Okay. Another reason one might be interested, other than just holonomy, is, as I said before, sort of every G2 manifold is Ricci flat. This is a classical theorem of Bonan. Okay. How would you prove this? Well, there's a straightforward way of you take the Ricci tensor and you just compute, you use kind of G2 geometric identities forever, and then eventually you show that the Ricci curvature is in fact 0. Another way is maybe more abstract. You can do this sort of on abstract general representation theoretic arguments. You can think of the space of Ricci curvature tensors as a G2 module and decompose that into irreducibles. And then there are sort of some very general abstract arguments which show that the Ricci curvature has to be 0. Okay, but probably what you want is not holonomy contained in G2. Probably what you want is holonomy equal to G2. And so how would you get that? How would you get holonomy equal to G2? So there's 2 criteria that you could apply. Okay, one is Judah-Bryant, and it goes like this. Let's say you have a simply connected 7 manifold, Riemannian, and the holonomy is contained in G2. Then you get holonomy equal to G2 on the nose if and only if there are no parallel 1 forms other than 0, of course. So the way you prove this is by essentially an application to Bergers' list, together with, again, the holonomy principle relating to the presence of parallel 1 forms in tensor fields. What you'd like to do is again, apply Bergers' list. So you need to argue that your metric, if there are no parallel 1 forms, you want to argue that your metric is not locally symmetric and not locally a product. Okay, and that can be achieved by the holonomy principle and sort of working out some cases. And then you can, again, appeal to Bergers' list. Okay, so another criterion, which is also very important in the compact case, is due to Joyce. And it says that if you have a compact manifold, not necessarily simply connected, and the holonomy is contained in G2, then you get holonomy equal to G2 on the nose if and only if your fundamental group is finite. Okay, and again, this is, if I recall correctly, an application of Bergers' list, but here you also need to apply, I believe, the Cheeger-Gromall splitting theorem. There's a proof of this written out in detail in Joyce's book, for example. So the strategy for if you wanted to construct compact manifolds with holonomy equal to G2 is as follows. You want to, or not even compact, just any G2 manifold, you want to sort of proceed in these two steps. So first, you want to find a torsion-free G2 structure, right? So you want to find a G2 structure solving this nonlinear PDE system. At first glance, this looks like a linear PDE system since d phi equals 0 is linear, but this second equation here is in fact nonlinear because of what I said earlier, that star depends nonlinearly on phi. So the second equation really is nonlinear. But if somehow you're able to find a torsion-free G2 structure, then the holonomy reduced metric is contained in G2. And then if you want holonomy on the nose equal to G2, then you can apply one of these two criteria. Now, there are known topological obstructions to the existence of G2 holonomy metrics. Here are some obstructions which are known. The fundamental group has to be finite. The third Betti number has to be at least 1, and the first Pontryagin class has to be non-zero. Okay, but we are currently very far from knowing necessary and sufficient conditions for a compact orientable spin 7 manifold to admit G2 holonomy metrics. We don't really know what the conditions would be at all. Okay, we now have sort of constructed many, maybe millions of compact 7 manifolds with holonomy equal to G2, but I don't know whether kind of any obvious necessary and sufficient conditions have really, or conjectural necessary and sufficient conditions have arisen from this massive list that has been kind of constructed. Okay. Now, as far as solving this PDE system, this is not easy. I mean, it's been done in many cases, but it's certainly not a trivial thing to do. And pretty much all of the examples come from one of these two ideas. One is that 7 equals 6 plus 1, and the other is that 7 equals 4 plus 3. Okay, what I mean more seriously by 7 equals 6 plus 1 is to use the inclusion of SU3 into G2. Okay, I'll talk more about that inclusion in the next lecture, but the inclusion of SU3 into G2 is very fundamental. And it suggests that you might be able to build a 7 manifold somehow from Calabi-Yau 3-folds or nearly Kähler 6 manifolds, which of course we'll talk about more next time. Another option is to use 7 equals 4 plus 3, and this refers to either the inclusion of SU2 into G2 or the inclusion of SO4 into G2. The inclusion of SO4 into G2 is somehow very well, that's a very, very fundamental inclusion for the study of associatives and co-associatives, for example. So let me give sort of the classic, now classic examples. So the first examples constructed were local and abstract due to Bryant. He showed that on small balls in R7, G2 holonomy metrics exist. In the same paper, he showed that on small balls in R8, spin 7 holonomy metrics exist. And he did this using a theory known as exterior differential systems, or Cartan-Kähler theory. And it wasn't just an existence theorem, but also a what's known as a local generality theorem. He proved that the generic metric depends on 6 arbitrary functions of 6 variables in the sense of EDS up to diffeomorphism. Okay, so what does this phrase mean? 6 arbitrary functions of 6 variables? What it means is that you can construct the generic metric by solving essentially a Cauchy initial value problem, where the initial data you get to arbitrarily specify consists of 6 arbitrary functions of 6 variables. Okay, so you can build your G2 holonomy metrics by solving this Cauchy problem, and the solution is essentially some sort of formal power series, and the point is that this power series converges. So you get real analytic metrics this way. Robert Bryant also constructed the first explicit example of a metric with holonomy equal to G2. His example was a cone. Okay, so he considered the flag manifold. This is a 6 manifold SU3 mod T2. We're going to look at this again next lecture. And this flag manifold has a certain homogeneous metric. It's what's called a nearly Kähler metric, putting this term in red because we haven't defined it. And the point is that if you take the cone over the 6 manifold, so that's R plus times the 6 manifold with the cone metric, it turns out that this has holonomy equal to G2. And this is a special case of something more general, which we'll talk about more next time. But those examples were all local. That example was a cone. And so one might hope for complete examples. And the first examples of complete metrics were found just not too long after by Bryant and Salomon. And in fact, they found 3 one-parameter families. They also found a one-parameter family of a complete metric with holonomy equal to spin 7, but that's another story. The Bryant-Salomon metrics are, they've been used in many, many applications in G2 geometry, and they've been characterized from various sort of intrinsic geometric points of view. So what are they? They arise as smooth manifolds. They're defined on the total spaces of vector bundles. So this is sort of this 7 equals 4 plus 3 idea. So one of the examples is a rank 3 bundle over S4, one's a rank 3 bundle over CP2, and another is a rank 4 bundle over the 3 sphere. Okay, so that's a smooth manifolds. And geometrically, you can build these things by imposing some geometric ansatz. You can require that the metric be a bundle metric, so it's of this form. Here, alpha restricts to the fibers to be the flat metric, and R is just the radius in the fibers. And essentially, by construction, these metrics are cohomogeneity 1 under an appropriate group action. And at infinity, these are all asymptotic to G2 holonomy cones. Okay, so these are somehow models of like a desingularized G2 holonomy cone. And we'll talk more about G2 holonomy cones next lecture. I know I'm hinting at many things we'll talk about next time. Okay, so these are very, very fundamental examples. And then finally, I should mention that in the 90s, in 96, Joyce succeeded in constructing compact manifolds, 7 manifolds with holonomy equal to G2. And the idea is to perturb a closed G2 structure that is close to being co-closed. So Joyce proved this very powerful perturbation theorem. And as far as I know, every known example of a compact 7 manifold with holonomy equal to G2 uses Joyce's perturbation theorem in some way. So the idea is that if you have a compact 7 manifold with a closed G2 structure that's close to torsion-free, you hope that you can perturb your G2 structure into one that is genuinely torsion-free. So to state the theorem, I'll just introduce some terminology. This is not standard. We'll say that an almost G2 structure is a pair consisting of a closed G2 structure phi and a 3-form psi, such that d star phi is equal to d star psi. The intuition, I'm told, is that psi is somehow a first integral for phi. It's somehow you somehow want some stand-in for d star phi. And so the perturbation theorem goes like this. So you fix positive constants A1, A2, and A3. Okay. Then the theorem is that there exists an interval, non-trivial interval, 0, capital T, and a constant K with the following significance. If your compact 7 manifold has a 1-parameter family of almost G2 structures, this should be almost G2 structures, and they satisfy 3 reasonableness conditions, then you can perturb your family of almost G2 structures into genuine torsion-free G2 structures. And these perturbed ones are C0 close to the original ones. Okay, now what are these 3 reasonable conditions saying? B is saying that you're allowing your family to degenerate, and C is saying you're also allowing your family to degenerate, but the degeneration as T goes to 0 is controlled. So the injectivity radius is allowed to go to 0, but it can't go to 0 too quickly. And the curvature is allowed to blow up, but it is not allowed to blow up too quickly. And moreover, this first integral, this psi, is going to 0, and it's going to 0 sufficiently quickly. So this is sort of a good thing. A is sort of saying that psi t is going to 0 kind of reasonably fast. So the intuition is that maybe you have your one parameter family and they're degenerating as t goes to 0, but somehow on the one hand, they're degenerating, the injectivity radius may go to 0, your curvature may blow up, but somehow also they're becoming closer and closer to a sort of degenerate torsion-free G2 structure. That this is a singular perturbation type theorem. Okay, the issue here is that finding inputs to this theorem is not trivial. Right, so Joyce's perturbation theorem is very powerful and certainly difficult to prove. You need some hard analysis, but you also need to worry about finding inputs. You need something to feed into the theorem, and that's not so simple. You need to find compact 7 manifolds with a closed G2 structure such that d star phi is small. Okay, that's a tricky thing to do, but examples have been found. Certainly, the original example was by Joyce in his so-called G2 Kummer construction. The input was essentially a flat orbifold. You take a 7 torus with its flat metric, you quotient by some finite group of isometries, and then you resolve the singularities, and then those are your inputs. A rather different construction is the twisted connected sum construction due to Kovalev, and then greatly extended by work of Corti, Haskins, Nordstrom, and Pacini. And this is sort of a 7 = 6 + 1 idea, where you take a Calabi-Yau and a threefold, which is, I believe, asymptotically cylindrical. You cross it with S1, and you take a pair of such things, and you want to glue them together in some twisted way that interchanges the factors. So you need asymptotically cylindrical Calabi-Yau threefolds to make this work, and there's been a lot of work done on that, on the building blocks needed for this to go. And recently, Joyce and Karagiannis, based on Joyce's construction, they found some sort of analog of the G2 Kummer construction where you can resolve the singularities. You have sort of a different type of singularity structure, and you can resolve it using, you can glue in certain families of Iguchi-Hansen metrics. Shouldn't talk too much about things I'm not expert in. But anyway, sort of some open questions are these. If you have a compact 7 manifold with a closed G2 structure, does it also admit a torsion-free G2 structure? This is not known. So every 7 manifold that we know that has a closed G2 structure, either we've been able to perturb it to a torsion-free one, or we don't know if it has a torsion-free G2 structure at all. A related question is whether the 7 sphere admits a closed G2 structure. This is not known. So it is known that the 7 sphere cannot admit a torsion-free G2 structure for topological reasons, but it could, in principle, admit a closed G2 structure. This is sort of a very basic thing to want to know, and this would, in a sense, answer the previous question in the negative if the 7 sphere really did have a closed G2 structure. And a very broad class of questions really is how can we distinguish 7 manifolds with G2 holonomy? How can we tell them apart? What you'd like is to have invariants that would, tell G2 holonomy manifolds apart. And one way of constructing such invariants you might hope is through either analyzing gauge theoretic objects, and indeed there's a whole kind of theory of gauge theory on 7 manifolds with holonomy G2, or more generally torsion-free G2 structures. There are various different gauge theoretic objects that have been considered, G2 instantons, G2 monopoles, deformed G2 instantons. I won't go into those. And hopefully one might be able to construct an invariant using these gauge theoretic ideas. But on the other hand, you might also hope that you could distinguish these 7 manifolds by counting special submanifolds inside of these things. So you might hope that somehow a moduli space of special submanifolds analogous to the Gromov-Witten story in symplectic geometry might work. So maybe you would, you hope that moduli spaces of distinguished submanifolds would somehow lead to invariants of torsion-free G2 structures. I'll hint at that a little bit next time, but I think maybe this is a good place to stop because otherwise the time for the next lecture will be a little awkward. So next lecture, we'll pick up here with the special submanifolds and then talk about nearly Kähler 6 manifolds and finally holomorphic curves. So thanks.
All right, thank you very much. Any question? You can unmute yourself and ask question. All right, then we're gonna meet 2:30 in the afternoon. Thank you very much for the nice talk, and see you in the afternoon.
Okay, thanks, bye.
Bye.